In this video, I'm going to explain two important concepts. I'm going to explain the concept of a moment of an area. Then I also explain the concept of a centroid of an area. The moment of an area is analogous to something like the moment of a force, where we multiply the force by a distance from a certain reference point. When it comes to the moment of an area, it is the area times a distance from a reference axis. So when it comes to the moment of an area, we have a reference axis, which can either be the vertical axis, the y-axis, or the horizontal axis, which is our x-axis, or it can be any other axis that we can choose to be our reference axis. So the moment of an area is the area times the distance from the reference axis. But I want to zoom in a little bit into this distance here. This distance here we called r. It is not really a whole distance. It is actually the distance from the reference axis to the center of that shape. From the reference axis to the center of that shape. This is the distance that we're talking about. I'm going to explain it further if I draw a shape. Then if we now talk about the centroid. The centroid is a point on a shape. And when you say this shape, it is a 2D shape or a flat shape. A shape that has no thickness, a shape that has no volume, a shape that has no mass. It is a flat shape or a 2D shape. These are the kind of shape that you've got centroids. So the centroid is like a center of that shape. It is a point where we can assume that the whole area of the shape is concentrated. If I'm going to use an analogy, the centroid is analogous to the center of gravity. But we apply center of gravity to objects that have got mass, to objects that have got volume, to objects that have got a thickness. But when it comes to a centroid, it is applied to 2D shapes like triangles, rectangles, and any other irregular shapes that we can think of that do not have mass, that do not have a volume. This is what we mean by centroid. So it has coordinates, an x coordinate and a y coordinate. If we're looking for the x coordinate of the centroid, we find the moment of area with respect to the y-axis. So this is the moment of area with respect to the y-axis, and this is the moment of area with respect to the x-axis. Once you have these, if you want the x coordinate of the centroid, you divide the moment of area of about the y-axis, you divide it by a, which is the area. And then the moment of area about the x-axis, you divide it by a, you get the y coordinate of the centroid. It's quite as straightforward as that. So what are the skills that you need? You need to know how to calculate the area of a shape, which is also an application of integration. So you should use integration to find this area. And in another video, I actually explained how you use integration to find the area of a shape, or if an area on a Cartesian plane that is enclosed by graphs or with the reference axis. I explained how you find that, but now in this video the emphasis will be more on how you find the moment of area with respect to the y-axis or with respect to the x-axis. Now this is the formula, and this is what the formula says. If you use this formula here, or these two formulas, if you have if your area is enclosed by two graphs, it doesn't matter what they are. If they are reference axes, we know how to reference them or how to refer to them. So it will be, in this case, it's x1 minus x2. You multiply it by dy. If we are going to be a little bit more, if I'm going to explain this a little bit more, this part here is actually dA, which means it's a differential area element. It's a differential element of area, which also applies to this one. Now the r, as I said, the r is a distance from the reference axis that it is. So what r is going to be depends on the reference axis that you're dealing with. and other factors. I'm going to explain that in this video. So this is what we're going to be doing in this video. We're calculating the centroid or the coordinates of the centroid. Sometimes we just ask you for one of them, like the x coordinate of the centroid or the y coordinate of the centroid. This is the approach. This is how you do it. All right, let's go to an example. So this is an example here. It's question 5. It says sketch the graph of y equals to 2 ln x and y equals to 2x. So you're sketching these graphs on the same Cartesian plane and show the area bounded by the graphs, the x-axis and the line y equals to 2. So if we're going to sort of like analyze our question, it means here we are looking for an area here that has got 4 boundaries. It has 4 boundaries. The curve y equals to 2 ln x, y equals to 2x, the x-axis and the line y equals to 2. So it is very, very important that you be able to calculate or to sketch the area, by the way. You need to sketch this area on a Cartesian plane for you to do question 5.1.2. You cannot use integration to find this area if you haven't or if you didn't sketch the area properly. So after the sketch, we do question 5.1.2 where we find the area. We need the area if we're going to find this x coordinate of the centroid, because we need to divide our moment of area about the y-axis. We divide it by the area that we found in 5.1.2. Then we get this x coordinate of the centroid. This is how we're going to do it. So let me start now by the sketch. So I'm going to move to the sketch. So we have 4 boundaries, as I said. So let us come out here. Let's come here and do the sketch. So we are here. So we have y equal to 2 ln x, then y equal to 2x, then y equals to 2 and the x-axis. We are going to sketch our area bounded by all these. Let me confirm this. Let me confirm. I might have made a mistake. All right, so we have y equal to 2 ln x, y equal to 2x, y equals to 2 and the x-axis. This is what we are looking for. All right. Now let's come here. I want to draw my axis. I'm going to draw my axis. All right, so this is my y-axis. Then I have my x-axis, my horizontal axis. That's it. And then the graph y equals to 2x. This is a straight line that passes through the origin. So y equals to 2x is a graph like this. There it is. Then y equals to 2 is actually a horizontal line. So I'm going to draw y equals to 2. This is y equals to 2. There is y equals to 2. Then the x-axis, this is our x-axis, so I don't have to draw it again anyway. I can just trace here. This is our x-axis. Now we need the line 2 ln x. This is a logarithmic graph. The logarithmic graph passes through the point x equals to 0. In other words, x equals to 1. In other words, when y is equals to 0, x here is actually equals to 1. When y equals to 0, x is equals to 1. So we have this point here 1, where x equals to 1 here. So this is 1 for x. Okay, let me label my x. This is the x-axis. This is the y-axis. And now this graph is the logarithmic graph. This is how it will look like. Let me still use a yellow pen. So it will go like this. It will come like this. It passes through here. Then it goes like that. This is the line. So let me label all my lines. I'm going to use a green pen for that. So this is the line y equals to 2 ln x, and this is the line y equals to 2. This is the line y equals to 2x, and this is our x-axis. I already labeled it. So we have, this is the area. I'm going to shade the area using some blue ink here. So this is the area, all of this. This is the area that we're looking for. Guys, I'm already answering question 5.1.1 where it says sketch the area and show it. They also said something in the question. Let me pull this off. They also said, yes, show a representative strip. So I have to show the representative strip on my area. So I'm going to use a horizontal strip for a reason. I'm going to use a horizontal strip to represent my area strip. So let me do this. So yes, I'm going to show my representative strip. So let's show our representative. Okay, let us show our representative strip, which is a horizontal strip, by the way. So I have to draw this strip. So I draw a line here. Let me use a different pen. So I draw a line. Here I draw another line here. This is a thin strip. If you look at this strip, it has a thickness. The thickness of this strip is actually delta y. So dy is the thickness of the strip, and the length of the strip is x1, which is here, this x here. So it's x1 minus x2 minus the x here. So we have x1 here, we have x2 here, such that if I want to talk about the differential area element of the strip, it is actually dA. So dA is equals to x1 minus x2. This is the length times dy, which is the breadth of this strip. So this is the differential area element. We need it. We need to know about it so that we can deduce the function that we're going to use for our integration. This is very important. Anyway, question 5.1.1 is answered completely. We have sketched the area. We have labeled all the boundaries. We have also shown the representative strip. There it is. Now, when you are calculating the moment of area, and we said our reference axis in this time is actually the y-axis. What you're going to do here is you're going to measure a distance from the y-axis here to the middle of this strip, to the middle of the strip, or to the center of the strip on a horizontal line. That is what we're going to do, but that is not for now. For now, we are worried about question 5.1.2, which is about the area. So I just want to come back here again and explain how you approach this. You want to find the area. This area is made up of these small horizontal strips. So in this case, our x1 is going to come from here. This is where we get our x1. Our x2 is going to come from here. This is where we get our x2. And we are adding, or we are summing all these small strips from y equals to 0 to y equals to 2. We may not have to, remember here we know that y here is 2. And here we know also that y is 2. We don't have to know what is x here or whatever. It's not really important in this case to know the x values, because we are using a horizontal strip, which means our limits of integration are actually y value. So we know the value of y here, it is 0, and the value of y there is 2. So to get our area, we are actually integrating here from 0 to 2 with respect to y. Now, let us go to that now. So we come out here, let's come here. We said our dA is x1 minus x2 times dy. And I said if we want to find our area, we're going to integrate this from 0 to 2. So we can integrate here from 0 to 2. I want to repeat something that I always repeat when it comes to application of these definite integrals. If you are integrating with respect to y, your limits of integration, this 0 and 2, should also be y values. That's one part. The other part is that these ones should be functions of in terms of y. So this should be in terms of y. In terms of y. And we're going to rely on what we had. So we said x1 is coming from y is equals to 2 ln x. From here we should get our x1, this x1. So we make this substitute of the formula. If we do that, we have x, we divide by 2 first, so we have x is equals to e to the power y over 2. This is our x1 here. Then the x2 is coming from y equal to 2x. So we're going to make this x subject of the formula, which means x here, which is x2, by the way, will be y over 2. All right. For those who are not getting how I got this, maybe I should explain a little bit further here. So we divide by 2 both sides, we get ln x is equals to y over 2. If we're going to take out this logarithm, we raise both sides. We use e, the base e as our base, because ln is logarithm to base e. So if we take e to the power ln x, we get x, and here we get e to the power y over 2. This is where I got this. All right, now we have that. So what we need to do next is to replace x1 with these two values that we have here. So we're replacing x1 with e to the power y over 2, and we replace x2 with y over 2, and we do our integration with respect to y, our definite integration with respect to y. Then from there we can get the area that we're looking for. So let us go to that. This means a is equal to the integration from 0 to 2 of e to the power y over 2 minus y over 2, all this being integrated with respect to y. This is how we're going to get our area that we're looking for. We need the area, by the way. We use this approach in all our calculations. So the key thing is to be able to deduce the expression for the differential element of area. That's the first thing that you have to do. So now let's go to that. Let's finish up this. So I'm going to open a new page. Okay, so we said A, the area. So our area here, A, is equal to the integration from 0 to 2 of e to the power y over 2 minus y over 2. All this integrated with respect to y. Let's do y. If I integrate e to the power y over 2, I get e to the power y over 2 divided by half, which is essentially 2 e to the power y over 2 minus, if I integrate y over 2, I get y squared over 4. Now from here we got 0 and 2. Now we substitute our upper limit, which is 2. If we put 2 for y in here, so we have actually 2 e to the power 1, because 2 over 2 is 1, minus y squared over 4, which is 2 squared over 4, so it's like 4 over 4, which is actually 1, but I'm just writing it here, minus, now let's substitute our 0. E to the power 0 is simply 1, so it's like 2 by 1 minus 0. We punch this in our calculator to get our answer in units squared. That will be the area, units squared, or square units. That will be the area. So my answer is 2.437 units squared. 2.437 units squared. So this is 2.437 units squared. This is our area, and this is question 5.1.2. We're going to need this answer in 5.1.3 because to get our x coordinate of the centroid, we divide the moment of area with respect to the y-axis by this area. So now let's just go to the next question. Let's go to the next question. So the following question wants us to calculate the area moment about the y-axis. Very important here, so that you know which approach to use, because when you say about the y-axis, we mean that our reference axis is the y-axis. So we are calculating the moment of area about the y-axis. In fact, this is quite a leading question. If they had not told us to calculate the moment of area about the y-axis, we were still going to calculate the moment of area about the y-axis, because we need it if we're going to find the x coordinate of the centroid. We have to find that. Now, if we go back to the formula that I showed you at the beginning, if we come here to these formulas, if we're looking for the area moment about the y-axis, you multiply r, which is the distance from the reference axis to the center of this shape, or in this case we're going to rely on our let me come here, the r, let me use a different pen. The r would be the distance from here. So the r is the distance from here, the y-axis, to here, to the middle of our shape. This is the r, and that distance is actually an x value. It's an x distance because it's a horizontal distance. Now, how do we get this middle of this? We add x1 and x2. We add x1 and x2, and we divide it by 2. That's how we get our r. So our r is actually x1 plus x2 and divided by 2. This is very important. Now, and the dA from the formula is actually this one. We already have dA. We know it. So now I'm going to go to a brand new page and do this calculation for the centroid. Okay, so I'm going to do this calculation for the centroid. We said Amo-y, Amo-y, so Amo-y is equals to integration of r dA. That is what it means. Now our r, so this is integration, our r is x1 plus x2 over 2. And we are multiplying this by dA, which we said is x1 minus x2 dy. And guys, our integration is obviously from 0 to 2. Because if we use dy here, we're going also to use y values as limits from 0 to 2. Those are limits of integration. Now, from here, I can take out half. From here, I will take 1 over 2 outside. So this is integration of x1 plus x2, then x1 minus x2 dy. But for us to integrate with respect to y, we should also get expressions here in terms of y. And if we look at our expressions, they are in terms of x. We want expressions in terms of y. And if we're going to do a reverse engineering here, x1 plus x2, x1 minus x2 is actually equivalent to, so this is like 1 over 2 integration of x1 squared minus x2 squared dy from 0 to 2. It means this. Yet we know our x1 in terms of y. We also know our x2 in terms of y. So now let us go to, let us finish our calculation. So let us finish this calculation. All right. So x1, we know it. We know it from here. Let me put this off. We know it from here. We know our x1 from here. It is e to the power y over 2, and our x2 is y over 2. We know this. So we just have to substitute them back into that formula and finish the calculation. So we're here. So this actually means half integration from 0 to 2 of x1 squared, which is e to the power y over 2 squared, minus y over 2 squared. This all in terms of y. This is what we're doing. So if we square e to the power y over 2, we actually get e to the power y. And if we square y over 2, if we square it, we get y squared over 4. So let us finish our calculation. I'm going to go to a new page and show how you do this calculation. So let us come here. Let us come here. So integration of, so our Amo-y is equals to 1 over 2 integration of e to the power y minus y squared over 4 dy from 0 to 2. So this is 1 over 2. If we put 2 here, it's actually e to the power 2 minus 4, which is 2 squared over, sorry, I'm making a mistake. I have to integrate. If I integrate e to the power y, I actually get e to the power y. So this is e to the power y and minus e to the power, no, minus y cubed over 12 from 0 to 2. Now I'll substitute my values. So this is actually 1 over 2 times, I put 2 first, so e squared minus 2 cubed over 12, which is 8 over 12. I close this minus. Now I substitute 0, so it's e to the power 0, which is 1 minus 0. This is what I have, and I get my answer in units cubed. So this is actually units cubed. That's a matter of punching in your calculator and getting this answer that we're looking for. So the answer is 2.861 units cubed. 2.861 units cubed. That's the answer that we get here. 2.861 units cubed. Please note that this half is actually multiplying everything. Let me use a different color here. So the half is multiplying everything inside there. Please don't make that mistake. So the correct answer is actually 2.861 units cubed. So if I now have my Amo-y and my area, we know that the x coordinate, x bar, the x coordinate of the centroid, which we call x bar, is actually equals to Amo-y, the area moment with respect to the y-axis, divided by the a. That's all. So we know our a, we know our Amo-y, then we can find easily, we can find the x coordinate of the centroid. This is the approach. This is how you do these kind of questions. All right, now let us finalize that. Let's come here. Now x bar, as you said, x bar is equals to Amo-y over a. We know Amo-y, we just copied it. It is 2.861 units cubed over the area that we calculated. So we need to find the value of the area that we calculated. I think we have it here. Let's check. Okay, put this off. Let's put this. Okay. Anyway, these are the original formulas that we had, but now we need to calculate this one here, the x coordinate. It's Amo-y over a. The y coordinate is Amo-x over a. So if we wanted to find the y coordinate, we're going to find Amo-x over a. Same approach, just that we'll be using a different differential element of area there. All right. So let's come out here. We are here. So now our area was 2.437 units squared. I mean, so 2.437 units squared. That was our area. 2.437 units squared. If we divide these two, we get the x coordinate of our centroid, which we wanted, by the way. So it's 2.861 divided by 2.437. We get 1.174 units. 1.174 units. To 3 decimal places. This is the x coordinate of the centroid. It's a point on a Cartesian plane. It is an x coordinate and also a y coordinate. So it depends on your question on what they want you to find. In our case, we just wanted to find the x coordinate. We don't really have to say units here, as I said. We don't have to say units per se, but if you look at what we're dividing, you may want to call it units, but it's just a point on the line, which means it doesn't have to have this thing of called units. It's just a point on the line. All right, this is the approach. This is how you calculate the centroid. In other words, you learned 2 skills in this video. You learned how to calculate the moment of area, and you also learned how to calculate the coordinates of a centroid of a shape. That's what you learn to calculate. Maybe before I go, I just want to highlight something about the R, because that R can be problematic to many people. If we have these x's, let's say this is my x-axis and this is my y-axis, and I have this area here, which happens to be a rectangle, and this is my reference axis. The x-axis is our reference here. This R that we spoke about, it is the distance from this reference axis here straight to the middle of this shape. This is R. I want to emphasize this. It's a very important concept for you to understand. So this is R. This distance here is actually our R. This is the R that we have on a Amo. Area moment is equals to integration of R dA. This is R. dA is the area, so it's like this distance here times the area. So if we know this, that this is y1 and this is y2, R is y1 plus y2, plus y2 over 2 on a horizontal something. If on a horizontal x, if I draw a horizontal distance of R, which means in that case my reference axis will be the y-axis, which was the case in this question. Our R is this distance here. Let me use a green pen to highlight that. Our R is this distance here to the center of this. So this is our R. This would be our R, this one. And if you look at this R, if you know that this is x1 and this is x2, if you want to find this R, the R is actually equals to x1 plus x2 over 2. That's why you saw me when I was doing the calculation, I used x1 plus x2 over 2 for R, because the distance that we use is the distance from the reference axis to the middle or to the centroid of that shape. Remember, we don't know the centroid. So if this is the centroid of the shape, this will be the centroid of the shape, which is actually x bar. The coordinates here is x bar and y bar. That's the centroid here. So the R is actually a distance from a reference axis to the centroid. That is what we call R in all these things that we're doing. But if you look at what I have, it's a regular shape. I said it's a rectangle. But in real life, we don't find regular shapes always. Sometimes it can be a very irregular shape. The approach remains the same as long as you use integration. Thank you for watching the video. If you have any comments or any questions that you need clarity on, just write in the comment section below. Otherwise, give it a thumbs up and subscribe to the channel.